Early philosophers looked up and saw peace. Observing the endless, turning cycles of the sun and the moon, they assumed the night sky was eternal, unchanging, and entirely separate from the chaos we experience on Earth. The Greek philosopher Aristotle formalized this idea. He argued that Earth sat at the center of 55 perfect, transparent celestial spheres. According to his model, these spheres rotated in endless, predictable cycles, holding the planets and stars safely in a realm of divine order. That illusion of perfect order cracked in the year 1054. Stargazers across North America, China, Korea, and the Middle East spotted a blazing new light near a crescent moon. Similar massive explosions appeared seemingly out of nowhere in 1572 and 1604, burning bright enough to be seen with the naked eye. These sudden eruptions of light proved that the celestial realm was capable of violent, unpredictable events. Astronomers like Galileo used these exploding stars to build a case that the cosmos is dynamic, not a set of permanent glass spheres. The tranquility of the night sky is a deception. That quiet darkness hides an active, fiercely churning environment that our naked eyes simply cannot process. To actually see that cosmic violence, modern astronomers rely on the full electromagnetic spectrum. By collecting everything from long, low-energy radio waves to short, high-energy gamma rays, they can detect the invisible forces tearing through space. This technology gives us a front-row seat to the strange death of a giant star. When a massive star stops producing enough nuclear energy in its core to counter its own gravity, it collapses. The crushing pressure causes the star to erupt outward into a violent supernova, launching superheated gas and shockwaves thousands of kilometers into space. Once the billowing clouds of gas clear, a highly compressed core is left behind. If you took the entire mass of planet Earth and crushed it down to the size of a tennis ball, you would match the density of a spinning neutron star. In extreme cases, the core collapses so completely that it forms a black hole, an object with gravity so intense it emits no light at all. We detect them by watching what happens to the matter around them. As gas flows inward, it forms a spinning disk. This disk generates twisting magnetic fields that channel inflowing matter outward into a pair of high-energy jets, accelerating it to nearly the speed of light. There is a deep irony in this destruction. The explosive forces that obliterate giant stars act as cosmic hatcheries. The blast seeds the surrounding space with carbon, oxygen, and iron, the heavy elements required to form new solar systems and build the chemistry of life. On a massive scale, the energy from supermassive black holes actually regulates how entire galaxies grow. By launching those powerful jets into deep space, they heat up surrounding regions of gas, cutting off the fuel supply and stunting the growth of the central galaxy. For centuries, scientists assumed our Milky Way galaxy constituted the entire universe. Then, working with a massive 100-inch telescope on Mount Wilson, an astronomer named Edwin Hubble started analyzing fuzzy patches of light in the sky, known as nebulae. He realized these patches were not local clouds of gas and dust. They were entirely independent galaxies, massive islands of stars sitting millions of light years beyond our own. A second observation proved even more shocking. By studying the light from these distant galaxies, astronomers found they are actively moving away from us. The further out they are, the faster they are receding. If everything is flying apart, logic dictates that in the deep past, all matter and energy had to be clustered together. This observation gave rise to the Big Bang model, proposing that the universe expanded outward from a single, intensely hot and dense starting point. We were no longer living in a solitary, static cluster of stars. Earth was now understood to be a microscopic piece of an immensely vast, highly active, and constantly expanding web of galaxies. Yet, the standard Big Bang model had a major flaw. When astronomers measure the spread of galaxies and the density of matter across the visible universe, the temperature is practically uniform. To achieve that exact temperature everywhere, the early universe would have had to expand much faster than the standard Big Bang mathematically allowed. This heat map shows the cosmic microwave background radiation. Captured by satellites like COBE, it represents the very first microwave light emitted when the universe was in its infancy. Look closely at the tiny red and blue fluctuations. These spots represent the primordial seeds of the cosmos. They map the early density of matter that gravity eventually amplified into the vast structures of modern galaxies we see today. To explain why this map is so uniform on a large scale, scientists proposed the theory of cosmic inflation. The idea is that in a fraction of a second, primordial energy fields tipped into a higher state, causing space and time to violently inflate, expanding instantly from the size of a microscopic atom out to immense cosmological proportions. The mathematical reality of inflation points to a staggering scale. If the theory holds true, the universe grew so rapidly that the entire observable universe we can map today is to the actual universe what a single atom is to our observable universe. Some versions of this theory suggest that inflation doesn't just happen once, but is an eternal process where different regions of spacetime branch off and stop expanding at different times. In this view, our reality is just one bubble in a vast foam of potentially infinite universes, all rising and expanding across a horizon we are only beginning to name. You can feel that staggering physical distance by looking at the twin Voyager spacecraft, launched in 1977. These human-made machines are currently traveling at 16 kilometers per second, plying the outer limits of our solar system tens of billions of miles away. Even at that incredible speed, the timeline for space travel is humbling. It will take Voyager nearly 300,000 years just to pass within 4 light-years of Sirius, a neighboring star. We are separated from the rest of the cosmos by scales of distance and time that completely eclipse our physical reach. Yet, our intellectual reach spans billions of light-years. From a tiny corner of the Milky Way, we have managed to observe, measure, and map the underlying scaffolding of time and space. Every element in our bodies was forged by the same violent engine that shaped the galaxies. While we are physically confined to a tiny corner of the Milky Way, the fact that we can map the structure of the infinite connects our small world to the very forces that transform the universe.